Hey, what's up, guys? So this is the last lecture about this quantum circuit, basically chapter for Niels and Chang. But I want to provide more results, which is it's not covered in the textbook. Okay, so remember the full idea of the main message of chapter 4 of this quantum circuit is that because we cannot write we cannot produce any n-qubit unitary efficiently. Uh, so technically, we then build so-called approximate quantum universal gate. One particular set is the Hadamard gate and CNOT gate, and also the so-called pi over 8 or T or so-called T gate. Oh, so these are like the proof is using the Weyl equilibrium theorem and the multiple types of decomposition. Okay, so the next question is that can we further reduce this guy to can we further reduce? We have like three gates. Can we like further reduce? Maybe can we reduce to because this is two qubit, right? So can we like reduce to two of them? Let's say you take some single qubit and some two qubit gate, okay, or three qubit gate. Okay, can we do it? Okay. So this is like more recent, more like 20 years. 20 years ago, there's a new results that actually we only need two. Okay, so I will explain the detail. And I also want to give some example of this quantum circuit of the application of quantum circuit. Okay, so the first interesting results is basically no need imaginary. So this is not in textbook. So one might ask. So one thing I will say is that one can ask whether Hadamard C not case is universal or not. Right. So this is the open question that we have not yet answered. Is this guy universal? So naming that if you give me one particular unitary, can I use the product of Hadamard and C not such that their Euclidean norm is arbitrarily small. Okay, and one particular answer, one might say, oh, it's impossible, right? The reason is that Hadamard, all the matrix element of Hadamard is real because it's 1 over square root of 2, 1, 1, 1, minus 1. And for C naughts, they're all real, like 1, 1, 1, 1, right? In terms of matrix element, if you pick particular basis. And so they are all real, right? There's no imaginary, and the imaginary number is somehow like in the heart of the quantum mechanics, right? Because in the Schrodinger equation there's I, right? So this I will make the wave function the normal wave function to be fixed. So if I claim that the absolute value of square of the wave function is a probability, then this I is necessary to be there. Okay. However, this is not true in this quantum circuit. So this is what I want to talk. And after that, we will talk about so-called Bell measurement and quantum interpretation. These three are like quantum circuit application. Okay. Okay. So recall so-called Toffoli gate, which is also called a control not. Basically mean that if the first two bit is one, then reflect the third qubit. So mathematically, you just write the x1, x2, and 3 if the and x3 plus or and, it should be and. Sorry, this is exclusive or. So x3 exclusive or x1 and x2. So that means that if x1 and x2 are 1, then you will add 1. So basically, it will flip. Okay, and I say that as I mentioned in class, that Toffoli gate is classical universal. The reason is that this is Toffoli gate, right? So if you fix the third bit to be 1 and first two bit A and B, then output bit will be 1 plus A and B. So this is the NAND gate of AB. Okay, and we know that NAND gates, right? NAND gate is classical universal. This is easy to prove because you can use NAND to build and then use NAND to build NOT and NAND to build OR, and you can prove proof is classical universal. So Toffoli gate is single 3-qubit gate, but it's classical universal. Okay, so we now are interested in so-called real gates. By the way, these Toffoli gates are real, right? Because these are bits, so they are real. So we want to ask, for example, let's say 3-qubit unitary gates with matrix element, a real matrix element. This is a set G. Okay, so basically they are all real orthogonal matrices, and cannot approximate any complex number, right? Definitely. Okay, but amazingly, it's computational equivalent to universal gate sets. So namely that if you define BQP using G, and it's the same as BQP with universal gates. Okay. So this is the so-called weak simulation. So the idea basically is that suppose you only have real gates, but it's fine that you can allocate a new extra qubits and using these extra qubits to represent a complex number. So theorem says that if I give you the n-qubit state and a unitary U, and some for measurement, there exists a so-called weak sampling. So weak sampling basically means that you have two probability. Weak sampling basically mean that you can give you a circuit C, you can create another circuit C prime, such as C prime as the output measurements probability distribution of C prime is the same as probability distribution of C. So this, if you give me n qubits, I can use n plus 1 qubit with real amplitudes. So now these states can have complex information, and this unitary can be complex. But the new circuit has extra 1 qubit, but all the amplitudes are real, and the gates are all real. Okay, so this is the proof, and this is the statement. And basically, all the measurement constant depths can also using a real. Oh, so the proof is interesting. We start with any complex any states, right? Let's say psi equals to x, alpha x, x. So we need to use a n plus 1 qubit, extra one, right? So we can write real alpha x into real imaginary. So we use a 0 as a x basis. Sorry, the real axis, and it is 1 as imaginary axis. So we decompose this alpha x into real alpha x0 plus imaginary alpha x1, and a tensor with the extra x. So this is n qubit. This is the first qubit, and then you sum over x. Okay. So notice that this map is non-unitary and basis dependent, but it's fine. Yes, and we fix some computational basis. Somebody gives me state, then I create this n plus 1 real amplitude state. Okay, so this is the state encoding. Now we want to simulate U, right? We want to simulate U. So somebody give me U. I define a U tilde, which is the n plus 1 unitary on n plus 1 qubits. Okay, so this looks weird, but yeah, just remember it, and we will see the calculation. So when U tilde acts on 0 tensor X, like, right? So I can write U in terms of real plus imaginary, right? As a matrices. Okay. Now this is the two matrices, the matrix acting on the n qubits. These are matrix acting on the n qubits. Right, so when I define U tilde acting on 0 tensor X to be 0 tensor real part of U acting on X. And for 1 is imaginary acting on X. Okay. And then for U tilde or 1 acting on X, I use a -0 imaginary acting on X and 1 real U acting on X. So you can view I construct a larger matrices. Basically, it's real U, imaginary U, minus imaginary U, and real U. So this is similar as rotation matrices. Okay. So the lemma says that if you give me the state encoding, the new state is tilde, U tilde acting on the psi tilde is the same as U acting on psi, and do the mapping, do the state mapping. Okay. So yeah. Okay. So this is the thing we want to prove. So what this means that you can if you have multiple unitary apply on psi, this psi can map into the real one, and all the gate can map to real one, and these are compatible. Okay, so the proof is basically this. Okay, so the proof is we first compute left hand side. So left hand side. So this stage side tilde is here. Okay. Sorry. No, it's not. A bit too fast. So let me see. So right. So let me just write outside. Right. So side tilde is a. So when we do computation, we can just neglect about this x because we know it's linearly, right? So it's real u. Sorry. Alpha x real part 0 plus imaginary alpha x 1 and tensor with x. Okay, right. So this is this. Okay, so when you apply on 0 tensor x, you get 0 tensor real and 1 tensor imaginary. Right, so we collect, so this is here, coefficient for real part. And for the imaginary part is imaginary, and the utilize minus 0 tensor imaginary plus 1 tensor real. Right, so minus 0 tensor imaginary plus 1 tensor real here. Okay, so now we can collect everything, right? Let's say we collect the real part, so we collect these two real x. Right, so we get here, and the previous coefficient is alpha, a real part of alpha x 0 plus imaginary alpha x 1. So it's here. And similarly for imaginary part, we get real alpha x 1 minus imaginary alpha x 0. So it's here. Okay, so hopefully you can just check it by yourself. Yeah, but I type it so that it's not so difficult. Okay, so that I can easily present. Okay, so this is the left hand side, right? So how about right hand side, right? So right hand side is, let's say we take u apply on psi. So what's u apply on psi, right? So whatever it is, right? So we just write down. So it's real u plus I imaginary u. Oh my God. I see it? Okay. So apply on the real alpha x plus I imaginary alpha x summation x. Right? This is the calculation. So we just compute, right? So we take the real part. So it's real minus 2 imaginary, right? So real minus 2 imaginary. And the cross term is real and imaginary plus imaginary and real. So it's here. Okay. So now we do the mapping again, right? Remember the mapping using extra 0 to encode the real part and using 1 to encode the imaginary part. So for this guy, which is real, we use extra 0, right? Now this is real, right? This is imaginary, right? So when we were mapping, we use extra 0. So here is 0, here is 0, here. So let me see. Here, right? We take the real part and using 0 and 1 part, imaginary using 1, right? So let me see. Okay, so this is real, right? So we use extra 0 here and compile 0 here and extra 1 here. 1 here. And then we neglect this I. Okay, so now let's see what's the real u what's the real u acting on x? What's the coefficient between? So real u has this one and this one. Right, so we get real alpha x0 plus imaginary alpha x1, which is here. And for imaginary u, we get minus imaginary alpha x0 plus real alpha x1. So it's here. Okay, so if we compare it, we get these two are the same. Real and imaginary, real minus imaginary, real plus imaginary, real minus imaginary. Okay, nice. Finish the proof. Okay, so this is a proof. And so for the measurement, right, if I measure state psi tilde, I get 0x with real alpha x squared. I get imaginary 1x. I get 1x with imaginary alpha x squared. And I can discard extra qubits. So it's the same, right? Real plus imaginary. So that means that this G simulate any unitary quantum circuit preserving a PQP. So that means that you don't need imaginary. You can just using a single extra qubit to remove this imaginary. Okay, so zero, you don't need imaginary. Okay. So from this that we now have a power, right? We have extra power because there's a because now there's a I can use this method to further reduce the gate set, right? Because now Hadamard, C naught, and T, right? This guy is imaginary, right? This guy is imaginary. So, but but it's one qubit, right? So by the previous method, we should use three qubits. So the first thing we need to do is we need to combine these two using a two qubit. Combine these two with, using another two qubit gate. The reason why we need to use is that somehow this kind of method need to use three qubits, right, in general. So we hope to combine this with another two qubit gate, but with imaginary numbers, so that we can use this imaginary method. Okay, so we know that these three are approximate universal. See the previous lecture, and so we now reduce three gates to two gates. So we want to combine this C9 T over pi over 8. Okay, so this is the gate that I want to use. It's basically Hadamard gates. So Hadamard is preserved, and the C9 T pi over 8 I combine with so-called control. So-called this is called control phase gate. Okay, so remember, let me just recall the phase gate for you. So S is phase gate just 1, 0, 0, I. So it's very simple when S acting on 0 is a single qubit gate, acting on 0 is 0, acting on 1, give you extra I. So S0 is 0, and S1 give you extra I. Okay, so in terms of, but we use control, right? So it's two qubit gates. If the first qubit is 1, then you apply S to the second qubit. So mathematically, you can write as this. CR is the control phase gate, meaning that if the first qubit is 0, then I apply identity to the second one. If the first qubit is 1, I apply the S gate, which is control phase. So the phase gate apply on the second one. Okay, so writing because they are all diagonal, so in terms of matrices, it's just very simple. Diagonal of 1, 1, 1, I. So let me just using CS1 to be my shorthand notation. Okay. So my claim is that this simple 111I can give you the T gate. Okay. Okay. So first thing I want to claim is that C naught can be easily using this control phase gate. And it's very simple, right? Because if you square it, you get 1, 1, 1, minus 1, right? So this is the control Z. This is the Z gate, the poly Z. And you can conjugate with Hadamard. Hadamard give you from poly Z to poly X, right? So Hadamard ZHD is X, right? So if I square it, I square the control phase gate and conjugate this by using two extra Hadamard on second qubit, then this will give me control X. Okay, so it's very simple that if I have Hadamard and control phase, then I can create C naught. Okay, so this is the first step. Now the problem is this T, which is pi over 8, right? This rotation is weird, so we need to do some extra trick. So the idea is that suppose I want to I give you I initialize my state into the following. Let's say plus state tensors any state psi. This is plus. This plus state is easy to do, right? Because I have Hadamard, so I can do plus state. Okay. Then I apply the control S gate, then I get the following, right? Because for 0, there's nothing. For 1, I apply S to the second. Let's say psi is a single qubit. Okay. Now this is X basis. Just recall that plus or minus is 1 over square root of plus 0 plus or minus 1. Okay, so now I project into plus state. So I see I measure the first qubit at the plus or minus 1 basis. Okay. So in here that this is 0, you get psi. Project 1, you get S psi. So the total projecting state is 1 plus S acting on psi. So effectively is identity plus S gate, identity plus phase gate, right? So right, so it's half of identity plus this S. Okay, so identity plus S. So it's identity. Right, you can view as this. Wait, hmm? Hmm. Okay, so let's see. So we got 0, 0. So I got the 1 divided by 0, 1, 0, 0 half 1 plus I. So I divide by 2, divide by 2, divide by 2, divide. So this is the states. Okay, so we can just write it as 0 1 1 0 0, and then this is 1 plus I, right? So 1 plus I is square root of 2 exponential I pi divided by 4 divided by 2. Hmm? Right? Or let's see. Oh, so uh, so so this is not unitary. We need to do a normalization, right? But it's you can just see the phase, right? You can see the if you once you do a normalization, you can see the phase difference between this and this. Hmm. So this is exponential I pi divided by 4, right? This is exponential I 0. So there's a phase. There's a phase relevant phase. Sorry, the relative phase, which is pi divided by 4. So this is exactly the t. Right? So remember the pi over 8 gate is defined to be 1, 0, 0 exponential I pi divided by 4. So uh so I don't do the normalization carefully, but you can do a normalization. So you will get you can see the phase, right? You can see a relative phase between this guy and this guy, which is exponential I pi divided by 4, which is here. So this is the same as t gate. Probably this is incorrect. Right? I don't care about it. Okay. So yeah, you get a t gate. This is correct. This is correct. Okay, so you get t. Okay. So that means that you can get Hadamard using the control Z gate, sorry, the control phase gate, which is universal. So Hadamard with control phase gate. Okay, so now phase gate control phase gate is 1 1 1 I. Okay, so now we can use the previous method. We can use another 3 qubit gates another 3 real qubit gates to approximate these two complex 2 qubit complex gate. Okay. So finally I just say the results. So finally we will show final in the after this lecture that we hope to the rigorous proof that Toffoli gate and Hadamard gates are a computational universal for quantum computing. Oh, so idea is that we use real simulation on the control phase gate. Okay, and the final why this result is interesting because it tells you that actually Toffoli gate and Hadamard gate is universal. It's approximate quantum universal, but Toffoli gate is classical, right? So that means that the whole quantum computation is just original Toffoli gate, which is universal for classical, but you add the superposition, the power of superposition. Okay, so this is interesting because Toffoli gate is universal, right, for classical computation. Okay, so the proof basically using the previous this formula, right? This formula, this. So whenever I get 0x, I get 0 real and imaginary. When I get 1x, I get minus imaginary real. So you can remember this formula. So I suggest that maybe you do the calculation for yourself, but I will try to do it on the PowerPoint. So for example, I want to using real method to simulate real gate to simulate Hadamard. Okay, but this is simple because the imaginary of Hadamard is 0, right? So yeah, it's fine. Okay, so when x acting on 0x, then it becomes 0 and x acting on x. When it's 1, just one tensor h because everything is, so we only care about real part, so it's fine. Okay, so the resulting is basically a tensor with extra qubits, so it's fine. Okay, so the interesting simulating these are pi over 4. So the real part is 1, 1, 1, 0, right? And the imaginary part is 0, 0, 0, 1. Okay, so now we can apply this formula. Okay, so let me just do it for so this is the computational results. Sorry, for example, when x is 0, 0, we get 0. The real parts of 0. So for real parts, this real part is always be identity unless the x is 1, 1. When x is 1, 1, it gives you an extra 1. That's it. Okay. So when 0, 0, 0, you get 0, 0, which is identity. 0, 0, you get there's no imaginary, right? So you get 0, 0, 0. And for 0, 0, 1, when the first bit is 0, x is 0, 1, 0, 1, right? So when real part acting on 0, 1 is still 1. And there's no imaginary, right? So 0, 0. So you can see that when the first bit is 0, 0, 1, 0 is the same. Okay. You get 0, you get 1, 0, right? 1, 0, 1, 0. So these are the same. These are 1 and 1, 0, which is no imaginary. So the only difference the only non-trivial part is that when this guy is 1, the last two bits is 1, 1, 1, right? Because when it's 1, then there's no real part, but you get extra imaginary part, which is 1. So you get 1, 1, 1, 1, 1. Okay. You can just using this formula. Okay. So when the first bit is 1, the situation is the same. These three cases are exactly the same. The only non-trivial case is that when x is 1, 1, that you get minus 1 because you get extra minus 1 imaginary. So you get minus 0, 1, 1. And then there's no real part. Okay, so if you see these eight different results, then you can find a thing that the final results is basically very simple. If the last two qubits are 1, then it will control z gates on first bit. So if the last two bits is 1, then the resulting will just be a control z, or so the last two qubits control when they are all 1, they then apply the control z on the first bit. So the control I should say control x and control z. So you will need to first flip the bit, and when the bit is 1, you will not only flip but add the extra minus 1. So basically, simply speaking, it's basically control z plus a Toffoli, right? Control z basically means that if the last two qubits are 1, then I just apply the z. Then after that, I apply Toffoli. So if the last two qubits are all 1, I flip again. So control z is -1 on all three qubits are 1, and the Toffoli the last two qubit control in the first two qubit target. Okay, so that means that I can combine control flip the first two qubits when the last two are 1, then apply the phase. So basically all these are just control z plus a Toffoli. Okay, but notice that control z is very simple, right? Because I can use Hadamard to change z to x. So actually it's control x, but control x is Toffoli, right? So this is the relation. right. This is the I can just using control. I can control I can use Hadamard to change exchange Z and X. Okay, so that means that control at least control twice control Z can can be reproduced by Hadamard and Toffoli. So that means that everything is Hadamard and Toffoli. Okay. So first we proved that Hadamard and control phase are universal, but now we show that using this real gate method, finally Toffoli and Hadamard are already universal. Okay, so this is proved by 2002 and 2003. Okay, so this is final result is that quantum is basically classical plus a single Hadamard, plus the Hadamard gate. So this is why you heard some like there's some like a YouTube video says that the power of quantum computation lies in the superposition because Hadamard created a superposition. Okay, more or less this is true. Okay, in terms of this framework. Okay, and so Toffoli NAND gate is classical universal computation, so we can think the extra power of quantum computing comes just from the Hadamard gate. So that means, so in the next lecture that we will talk about some simple quantum algorithm. All these quantum algorithms, like four quantum algorithms, are based on the Hadamard gates. So we will see the power of this Hadamard gate in the next lecture. Also, this is the summary proof. Quantum is a magic classical 1 plus 1 Hadamard gate. Okay, so now I want to discuss like two simple examples of interesting quantum circuit. But I was think this is enough for this week lecture, so we will talk in the next week.